I will now talk about a very powerful algorithmic technique that we call divide and conquer. Divide and conquer is basically, it's a simple algorithmic technique, but very powerful. It says that if you want to solve a problem on some instance of size n, what do I mean by instance? Suppose you want to sort an element, an array of n elements. The instance is that array, the array of size n. If you want to work on a graph that has n nodes, that's the instance, the graph of n nodes. If you are trying to deal with a string with n letters, that's the instance of the algorithm. If I want to work with an instance of size n, I can divide it into b smaller instances, b subsets of that instance. Ideally, each of them of the size n over b. So we want them to be very close to each other in terms of size. So if you divide it into 5 pieces, we want these pieces to be each of size n over 5. And then some of these problems, some or all of them, could be solved. Okay, so we can now divide the instance into 5 pieces. You can solve all 5 of them, you can solve 3 of them, and so on, independently of each other. And then, if necessary, we can merge these solutions to the 5 pieces back together. Okay, in general, it's b, so we have an instance of size n. You divide it into b instances. You solve all b instances or subset of them, and then you might go back and merge the answers or group the answers of these b instances to get a solution on the original instance to the problem. I will now show 2 examples, textbook examples of the application of divide and conquer. One in which we divide the input into b pieces, we solve all b pieces, and then we merge the results from these b pieces to get the solution on the original instance. The other problem, we will divide the input into b pieces. We will solve only one of them, and we will never go back. We will never need to merge results. Okay? So the first problem is the sorting problem, and I assume almost everyone knows what sorting is. You are given an array or a list of n elements, and these elements, they should be, every 2 elements of them should be comparable so that I can say which one comes before the other. And I want as output, I want the list with the elements sorted in ascending or non-decreasing order. Okay? Now, brute force way to do this, which nobody implements this or nobody even thinks of writing sorting like this, but the worst brute force possible algorithm is to say, let me go through each permutation of the n elements and sort and check for each permutation whether they are sorted or not, and I can return the permutation that corresponds to a sorted list. Of course, if I give you a permutation and I ask you to go through it and check if it is sorted in ascending order, that's an O of n operation, because you can look at each element, check if it is larger than or equal to the element before it. The problem comes from the fact that there is n factorial permutations over a list of n elements. N factorial grows very, very fast. This is an impractical algorithm except for 3 or 4 or 5 elements and so on. So nobody would implement this algorithm. And as I said, divide and conquer is really a textbook example, or sorting is a textbook example of divide and conquer that gives us a very nice algorithm that's very fast. So here, what does it mean to do divide and conquer on sorting? The algorithm is called Mergesort. And imagine that we have an array of n elements, let's say 2, 1, 10, 5, 3, 4, 7, 6. So I want to sort this list, and I have many friends or many students in the course. I say, okay, I need help with sorting this list. The help will be by me saying, let me divide this array into 2 pieces, 2 halves. B is 2 here. So I'm going to divide it into 2 pieces of equal size. I'm going to give the left half to one student and the right half to another student. Okay? 3, 4, 7, 6. Now, each one of these students can now go to that terrible brute force algorithm and solve it. They say, now, Instead of 8, we have 4. This is better. Well, instead of n, we have n over 2. N over 2 factorial for large n. It is still a terrible algorithm that nobody would want to implement it. So these students say, well, let me repeat what Louis just did. And these students have friends. They say, okay, let me actually give my friends the left and the right halves of the array that I got. Okay, so 2, 1, and 10, 5. And the same thing with this student. They give to their friend 3, 4, and to another friend 7, 6. The same thing is going to happen. These friends, we have lots of students in the course. Everyone can keep doing the same and say, I'm not going to do work. I'm going to actually just divide and give it to others to do the work. So now we give it to 8 students. Each one of them is going to get an array of size 1. Okay. So 7, 6. So we divided the first instance into 2, and then each one of them into 2, and each one of them into 2. So now we have 8 students, each having an array of size 1. Everyone saying, with the instruction, please sort the array that you just received. Well, these students are going to say, I'm lucky. These arrays are already sorted. The student who got an array with one element 2, they say, the array is sorted. So check, it is sorted, and I'm going to send it back to the student who gave it to me. The same thing with the student who got the array with the element 1. It is sorted, check, I will give it back. And each one of them is going to do the same thing. Say, it is sorted, let me just return it to the student who sent it to me. Right? Now, when the student who sent it to them receives these arrays back from them, that student is going to merge them. But they're going to merge them in such a way that the resulting array is sorted. So this student here is going to get 2 arrays. One has 1 and one has 2. They say, okay, the way I should merge them is 1 comes before 2. So they're going to merge them like this. And this student here is going to merge them so that it is 5, 10. And this student here is going to merge them so that they are 5, 3, 4. And this student is going to merge the 2 arrays they got so that they are 6 and 7. Now, this student here, this student is going to receive 2 arrays. One is 1, 2. The other one is 5, 10. They need to give back an array with 4 elements. They need to merge it such that it is sorted. So what does this student do? They're going to start with the 2 arrays from the left, from the first element. And they're going to say which of these 2 elements is smaller. They will always take the smaller and advance that arrow or that reading head. So between 1 and 5, they say 1 is smaller. We'll put 1 here. Now this reading head goes to 2 because we are done with 1. Now between 2 and 5, which one is smaller? It is 2. Therefore, we are done here. So we are done with the first element. We say let's copy all the elements from the second array, 5, 10. The same thing here. This student here got 2 arrays. One is 3, 4, and one is 6, 7. They're gonna merge them. They're gonna do the same thing, going by from the first and the first. 3 is smaller. They will put 3 first. Then they will go to 4. 4 is smaller. They're gonna put 4. Then 6, 7. Finally, this original student that I gave the array to is gonna receive 2 arrays. The one is 1, 2, 5, 10, and another is 3, 4, 6, 7, and they're gonna merge into an array of 8 elements. And again, they're gonna start from the first element. 1 and 3, they say 1 is smaller, therefore I'm done. 2 and 3, they're comparing this to this now. 2 is smaller, so now they compare 5 to 3. 3 is smaller, they put 3 here. Now we go to 4 here. So 5 and 4 now comparing 5 to 4. 4 is smaller. We go to 6 now. 6 and 5. 5 is smaller. And now we go to the last one in the first array, 10. 10 and 6. 6 is smaller. So we now go to the last one. We have 7 and 10. 7 comes before 10. And if you look at this array, it is sorted. So to recap, we gave an array of size 8. We divided into 2 arrays of size 4. Then each one of these 2 arrays of size 4, we divided into 2 arrays of size 2. and then each one array of size 2, we divide it into 2 arrays of size 1, then we were done. These arrays of size 1 are sorted. We start going back. Okay, we start going back. So what I mean back and forth, notice that we went down this way. When we got to arrays of size 1, we started going back this way here. And if you look at this structure here, we have this node, it has 2 children. And each one of them has 2 children. Each one of them has 2 children. And if you look at them, what we have is a tree structure. On top is the root of the tree. At the bottom, we have 8 leaves in this tree. Okay? So this is how merge sort works. You go down by dividing every input into 2 arrays of half the size each, and then going back, merging these results. Okay? How do we write this algorithm in pseudocode? It's very simple. This is merge sort. Merge sort says, if n equals 1, don't do anything. If n equals 1, the array is sorted. But if n is greater than 1, what this is saying is, if you have L, this is L, the left half is A, the right half is B. Copy the left half into A, copy right half into B. Now apply merge sort recursively on the left. Apply merge sort recursively on the right. And when you get back the outputs from these, merge these 2 back into L. Okay, this is all this algorithm is doing. So this algorithm really, all it does, it just keeps dividing. Okay, it keeps dividing things and building this tree structure in the recursion. This function is really doing all the work. This function, merge ABL, it takes 2 arrays and 2 arrays that are sorted. Merge ABL takes 2 arrays that are sorted and sorts them back into L. So this is how merge sort works. Again, the assumption is that it is 2 sorted lists, A and B, and we want to get L that's sorted. What is written here, again, if you have A, if this is A, and this is B, and this is the C, we want to merge A and B into C. I is the index that we are indexing A by, and J indexes B, and K indexes C. So if you look at this here, we ask if AI is smaller than BJ, we move AI into CK, and we have to advance I, right? I now becomes I plus 1. If we copy from B, we advance J. In both cases, we have to advance K, right? So if the AI is smaller than BJ, copy AI into CK. If BJ is smaller than AI, copy BJ into CK, and we keep advancing them. Okay? These 2 conditions here at the end is just for the case where we have copied everything in A and we still have elements in B. What we do is just we copy all the elements from B to C. Or if we have copied everything from B but A still has elements, we copy all of them to C. Okay? So this is really the algorithm, the merge sort algorithm. And one of the questions, of course, what's the running time? And the running time, the way we reason about the running time here is using recurrences. So think about it as we had T of n is the running time of merge sort. But what is the running time of merge sort? Remember that it divides into each input into 2, each of size n over 2, and it called merge sort on them recursively, right? So we had merge sort. The input was of size n. It made 2 calls, merge sort, each on an array of size n over 2, and then said merge, right? And then we called merge. So each one of these, if this merge sort, if this one here takes T of n, whatever that T of n, I don't know, I'm trying to compute it. If this takes T of n, well, then this call should be taking T of n over 2, and this one should be taking T of n over 2. So we have 2 T of n over 2, plus the time that merge takes. Now merge is going to take 2 arrays of size n over 2 in the worst case, and it's going to merge them. It's going to walk across this. So it's going to take on the order of n operations. Merge, when you give it 2 arrays of size n over 2, is going to take on the order of n operations. So this is where we get this recurrence, that T of n is 2 times T of n over 2 plus O of n. The question is that what's the solution to this recurrence, right? Because this is not something I know how it grows. I need to get to something that looks T of n is n squared, n cubed, log n, and so on. One powerful tool that allows us to solve recurrences of this specific form is we call the master theorem. So the master theorem says, imagine that your recurrence has this form, f of n equals a of f of n divided by b plus c n to the d. It's very important to notice a few things here. B is the number of instances that you divide your input into. Okay, so in the case of Mergesort, B was 2. A is the number of instances that you solve from them. So A here was 2, so we solve both of them. And then C times ND into the D, C times N to the D here is 1 because it is taking O of N. Okay, so in Mergesort, it's O of N, which is basically C times N to the 1, where C is a constant. So if we have a recurrence of the form A times F of N over B plus C N to the D, it has to be of this specific form. You cannot have 2 to the N or anything like that. Then we can solve it like this based on the values of A, B, and D. If A is smaller than B to the D, then the solution to this recurrence is O of N to the D. If A equals B to the D, then the solution is O of N to the D log N. If A is greater than B to the D, then the solution is O of N to the log A to the base B. Okay, so this is the master theorem, and it's a very powerful tool. So if we come back to Mergesort here and we want to solve it, what is A? In this case, A is 2, because we are going to solve both subproblems. B is 2, and what is D? D is 1, because O of N means N is to the power 1. So now we need to look at A and B to the D. We notice that A, here 2, equals 2 to the 1. So the solution is, that applies to Mergesort, is this one. So T to the N is O of N to the D, which is 1 log N. So the running time of Mergesort is O of N log N, okay? Which is a very, very fast algorithm. The second example I want to talk about is binary search. And binary search, here you have a sorted list of n elements, and someone gives you an element, say, is the x in that array? Okay, the key issue here is that L is sorted, and someone is asking if x is there. You return true if it is there, false otherwise. Well, if it is sorted, and these are, imagine they are numbers, it's totally ordered. If it is sorted, and I'm looking for x, I look at the middle point in this array, somewhere in the middle here, and I ask, is x there? If x is there, I say, yes, it is there. True, return true, and done. If it is not there, and x is smaller than the element in the middle, it must be, if it is in the array, it must be on the left, right? So if x is smaller than the middle element, or the element in the middle of the array, then if x exists, must be on the left. So I can now go to the left. If x is greater, it must be on the right if it exists, so I go to the right. And this is what binary search does. You just go to the middle. If it is there, return true. If it's not there, if it is smaller than what's there, go left. If it is larger than what's there, go right. And this is really the pseudocode of binary search. If the array has just one element, you just see if x is that element. Otherwise, you go to the middle point here, the n over 2. You go to that middle point and check if x equal to that one. If it is, you return true. If it is not, and x is smaller than it, you go to the left half. And if it is larger than it, you go to the right half. This is all this algorithm. Okay? So what's the running time of this algorithm here? Again, we go to the same situation here. T of n, we said we divide n to 2 halves. But for how many of them we solve? We either go to the left half or to the right half, not to both. So it really just solve one of them. Then when we solve the left half or the right half, do we do any merge, or how much work do we do? Really just one. It's a constant. Okay, so it's O of 1. Right? So A here is 1, B is 2, and D is 0, because n to the 0 is 1. So now I look at 1 and b, which is 2, to the d, which is 0 here. 1 and to the 0, they are equal. So based on this, I get this one, which is O of n to the d, which is 0, log n, which is O of log n. So the running time of binary search is O of log n. And if you think about it, without the master theorem, you have an array of size n, then you go to just the left half of size n over 2, then you go to n over 4, then to n over 8, and so on. If you reason about the height of this tree, how many times you can keep dividing n by 2. So if you have 16 divided by 2, it's 8. Divided by 2, it's 4. Divided by 2, it's 2. Divided by 2, it's 1. So if you look at this, if you reason about it carefully, you will see that after log n divisions, you're going to get to 1. And the height of this tree is log of n. And the master theorem gives us log of n, so it's not a surprising result.